Now, if you remember from the beginning of the course, we talked about matrix addition, matrix subtraction, and matrix multiplication. Well, what you may not have realized is that when we're talking about matrix inverses, that's basically the idea of matrix division. Because just think back for a second to simple real numbers. For example, if I have 3 divided by 3, I know the result of that is 1. Another way to write this is I can say 3 multiplied by 1/3. I can pull the 3 from the denominator out into its own fraction. Now, instead of a division problem, I have a multiplication problem. But we know that this is also equal to 1. And of course, 3 and 1/3, they're reciprocals of one another. And if instead of using a real number like 3, we use a variable, so let's say we use the variable x. So instead of 3 here, we'll say x. And then over here, 1 over x, so multiplied by 1 over x equals 1. I could rewrite this 1 over x, because remember, this is really x to the first power. It's the same thing as x. Well, I can move that to the numerator, and this is the same thing as saying x times x to the -1. That exponent, if it's positive in the denominator, when we move it to the numerator, it becomes negative. It flips its sign. So we have x times x to the -1 equals 1. Well, this sure does look a lot like the multiplication of a matrix by its inverse. If we have the matrix A multiplied by A inverse, we know that that is equal to the identity matrix, which is the matrix equivalent of 1. And this is intentional. This matrix inverse idea, where I have A and A inverse, this is the concept of matrix division. It basically tells us that when I divide the matrix A by itself, I'm going to get the identity matrix. But instead of writing it that way, we say I'm going to multiply A by A inverse and get the identity matrix. So we really want to understand that that's what we're doing. This matrix inverse concept is the matrix division concept. And now we want to talk about another way to find the matrix inverse, because in the last lesson, we talked about finding the inverse by starting with the matrix A. Let's say we have been given the matrix A and we want to find A inverse. And we said that if we augmented A with the identity matrix I, and then we went through the process of putting A into reduced row echelon form, that we would eventually end up with the identity matrix I on the left, and the result on the right-hand side would be A inverse. That's certainly one way to find the inverse matrix, and we can always do that. But another way is to use determinants. And remember, we talked a little bit about determinants when we talked about the cross product earlier. Later on, we're going to have a whole section talking all about determinants. But right now, we just want to talk about a formula that we can use to find the inverse matrix, and it just happens to use the determinant. So the formula tells us that if we're given some matrix, let's say it's a 2 by 2, and so we have A, B, C, D for the 2 by 2 matrix. Remember that the determinant of a 2 by 2 matrix is what we get when we multiply the upper left by the lower right, so A, D, and then we subtract whatever we get when we multiply the upper right by the lower left, so B, C. This AD minus BC pattern is always the determinant of a 2 by 2 matrix. Well, the formula that we can use to find the inverse, A inverse, is going to be equal to 1 over the determinant of the original matrix A, and then just multiplied by a modified version of that original matrix. So to modify the matrix, what we do is we switch A and D. So these upper left, lower right values, we switch their spots. So we put D up here and A down here. And then B and C stay where they are, but we multiply them by -1. So we get a negative B and a negative C. This is another formula that we can use to find the inverse, as opposed to this method where we augmented the matrix with the identity matrix and then put it into reduced row echelon form. So let's take an example, and let's say we're given the matrix capital X, and it is a 2 by 2 matrix. Let's say it's -2, 0, 4, and 1. Then X inverse, so X inverse, is going to be equal to 1 over the determinant of this original matrix. Well, to find the determinant, we just take -2 times 1, that's a -2, the upper left times the lower right, Then we subtract whatever we get when we multiply the upper right and the lower left. 0 times 4 is 0. And then we're going to multiply that result by this modified matrix here. So we switch the places of the -2 and the 1, so 1, -2, and then the 0 and the 4 stay where they are, but their signs change. Well, we can't say -0, that just stays 0, but we can say here -4. And then we just simplify here. So for the fraction, we'll obviously end up with a -1/2 times the 1, 0, -4, -2 matrix. And we just have a -1/2 to distribute as a scalar. So x inverse then is -1/2 times a 1 is a -1/2, times 0 is 0, times a -4 is a +2, and times a -2 is a +1. So this is x inverse when we started with the original matrix x. Of course, we can always verify that this is the inverse by multiplying x by x inverse or x inverse by x. Remember, when we're dealing with inverse matrices, that the matrix multiplication is commutative. We should get the identity matrix either way because they are specifically inverses of each other, even though matrix multiplication is not normally commutative. So we can multiply x by x inverse or x inverse by x. We should get the identity matrix. That's a great double check. But the main point that we want to make here, and the reason that we're bringing up this formula feels not super great because it feels like something that we're just memorizing. But the reason that we're bringing it up is because we get this interesting insight from the fact that we have a fraction here with the determinant of a in the denominator. Remember that in math, we can never divide by 0, which means that we can never have 0 in the denominator of a fraction. The denominator of a fraction can never be equal to 0. So when we use this formula, what we see is that we suddenly have this rule popping out, that the determinant of the original matrix can't be 0, otherwise this formula isn't defined. Well, what do we really mean when this formula isn't defined? If the determinant is 0, that means we're going to be undefined here. This is a formula for the inverse matrix. That just tells us that the inverse isn't going to be defined. Well, if the inverse isn't defined, then that just means that the matrix is not invertible. And all of a sudden now, we have a test for invertibility. We can say that if the determinant of the matrix is not 0, then the matrix is invertible. But if the determinant of the matrix is equal to 0, then we say that the matrix is not invertible, which we have another name for. We call it a singular matrix. So for a singular matrix, it's not invertible. It does not have a defined inverse. We cannot find its inverse. And so the point is that this just becomes a great, simple, quick test for invertibility. Before we go doing a bunch of math, like for example, the math with this augmented matrix where we go putting the matrix into reduced row echelon form, we can just do a quick check here with the determinant. Does AD minus BC equal 0? If it does, I know immediately that the matrix is not invertible. So keep that in mind. We just said if AD minus BC is equal to 0, I know I have a singular non-invertible matrix. Of course, I could also rewrite this equation and say if AD is equal to BC by adding BC to both sides. If AD is equal to BC, I know I have a singular matrix. I could also divide both sides by B and divide both sides by D, and I could rewrite this as A over B equals C over D. If this equation is true, I know the matrix is singular. So again, going back to this matrix X here, if we're given this matrix -2, 0, 4, 1, I could say AD is -2 times 1, that's a -2, minus BC, that's 0 times 4, which is 0. And I see that this is equal to -2, which is not 0. I know right away the matrix is invertible. Or I could have done this method, AD equals BC. I could have said -2 times 1 is -2, 0 times 4 is 0. Because these are not equal, I know that the matrix is invertible. Or this method here, A over B, those are the values from the first row of the matrix. I would get -2 over 0 is equal to C over D, the values from the second row of the matrix, 4 over 1. so 4 over 1. On the right-hand side here, I get 4. On the left-hand side, I get something that is undefined. Well, some undefined value is clearly not equal to the defined value of 4. So because this isn't true, I know that the matrix is invertible. On the other hand, if we had had some matrix, let's say we have the matrix Z, and it's equal to, instead of -2, 0, 4, 1, we'll say -2 and 4, and we'll say -4 and 8, which you can clearly see I found just by multiplying the first column by 2. Well, in this case, if I apply these 3 tests down here, for AD minus BC, I'm going to get -16 minus a -16. That's going to give me -16 plus 16, which is going to be 0. Because that's equal to 0, I know right away this matrix is singular. It is not invertible. It does not have an inverse. Or I could have taken AD equals BC, and I would have gotten -16 equals -16. And because that's a true equation, I know right away that the matrix is singular. Or I could have taken the ratio. So I could have said -2 over -4 is a positive 1/2, and then 4 over 8 is a positive 1/2. And because those are equal, I know that the matrix is singular. So again, just going back to this idea that we can use the determinant as a quick test to determine whether or not a matrix is even going to have an inverse in the first place.